Have audio? What audio? All right, we'll handle it. Announcements. I don't think there are too many. We have an assignment due tomorrow. I have 4 office hours available today. I do have to meet with our grader for a directed study at some point. That will probably happen at 12, but I have availability during equal office hours and starting at 1 for people who have questions. How's the homework going for people I haven't talked to about the homework yet? Excellent. Computer scientists usually like speaking to the void or talking to yourself. Sometimes I wonder if I have schizophrenia and I actually am just sitting in a mental asylum and think that I'm a professor. Wouldn't surprise me, personally. That is the best thing to walk into. Yes. I owe you a study guide for the next exam by the end of the week, which we will take next Friday. It's close enough that I can start making that announcement, which is also kind of scary. I hope to have exams to you by tomorrow. I will apply a bit of pressure on the grader and try to make sure that you get those back. Because it's been a while now and we need exams back.
Happen by end of last week.
Yeah. Yeah. In a less hectic quarter, it would have been by the end of last week. Life is hectic for our poor grader. All right, last time we were talking about NPDAs, and this was our first example. I drew this out on the board, but it was relatively quick because we were close to the end of class. So I wanted to kind of pause and see if there were questions about how we constructed this. Do we recall the solution for this NPDA? How did we feel about constructing the NPDA? Did that go all right for people? I think I queried the class. It seemed like, for the most part, people understood what was drawn on the board, which was good. But obviously, like every other topic in this class, it requires lots of examples, lots of practice before the idea really sticks. So I guess we will move forward. There aren't questions, and get some more examples. Here's an NPDA. Last time we also talked about instantaneous descriptions. Remember, we used the turn style and the aspects of an instantaneous description. Let's go back to that just to be absolutely sure we are getting everything that we need. We have this triple. We have the state of the control unit that is the first element of the triple. The second is the unread portion of the string. So it starts out being the entire string, and then as we make moves, it becomes less and less of the suffix of that string. And then we have the entirety of the stack contents as the third of our triple. So given that definition, let's look at an NPDA and parse BAAB with instantaneous descriptions. So we decide on what color we want to use. For those who walked in, it's pen ink replacement day, which is very exciting. I have to mix blue and red. Which of those do we want? With blue. Usually the first one that runs dry anyway. Haven't used it in a while. All right, so let's write a triple, then a turnstile, then a triple, then a turnstile, then a triple until we have the AAB parsed. Start writing C on this. There's our initial. Continue this process. What is it? There's kind of a cold call error in the moment he wants to.
It's consistent now.
Did we go over instantaneous description form? Just
Very briefly. Yeah, we kind of defined it as to what the triples are.
okay.
So it defines the actual movement of this through the space, but in a different way than kind of drawing the edges Q0 to Q0 to Q0, because we don't necessarily know there are so many options in NPDAs. Oftentimes a single state will have 6 or more transitions, and that's just for a 2-character alphabet with self edges. So in order to remove the ambiguity of we went from Q0 to Q0, well, which edge did we take when we did that? The instantaneous description tells us here's a snapshot of everything at a moment in time. Then we'll have the next snapshot at a moment in time. So we can see which transition we took in order to get from one snapshot to the next snapshot. It'll be dictated by the rest of this instantaneous description. So for instance, we go from Q0 to Q0, read the very first B, because we're going to be taking that transition. So we read the B, the remainder of the string is AAB, and the stack now, since we added a 1 on top of it, is 1Z. And from this pair of instantaneous descriptions, it's obvious which transition we took. We had to go from Q0 to Q0, so that's a self edge. We had to read a B from here. The first character is gone, so we needed an edge labeled B. And then we had to do something that pushed a 1 onto the stack. So between that triple of information, that tells us exactly which transition. And it's a lot clearer than just saying Q0 to Q0. So here we turn style again. And we need the next triple that reads that A. The question though is which A do we read? We need to, now that we have, I guess this read of B. So when we read this A, there's a 1 on the stack. So we need to do a tuple that has the character reading an A and the top of the stack being the 1. So sure enough, that's what we should do. We stay in Q0, we read that front A, and we're going to pop the 1 off the stack. So again, we get a sense just by reading this about which transition we took. We had to read an A, we had to get rid of the 1 that was on the stack, and we had to stay in Q0. That isolates to this transition. And there are 6 transitions from Q0 to Q0. So it doesn't really tell us a lot when we say we went from Q0 to Q0 to Q0 to Q0 to Q1 or to QF and terminate it. We need to read this A. So we will turn style. We're in Q0. We read that A, so all that's left is a B. The A transition, when there's a Z on the stack, pushes a 0 onto the stack. So our stack reads 0Z. One last one. We're in, I guess there's still 2 to go. We're staying in Q0, we need to read the B. So there's nothing left in our string, and this will pop the 0, giving us back our bottom of the stack character. Then we need to make the transition to QF. There's still nothing left to read, and this pushes the bottom of stack character back on. We'll talk about how the way that I said this, we actually have options. And as long as we're consistent, it's okay. So you'll note that at the end of class in my example, I had a state to push on the bottom of stack character. You can reasonably assume that the bottom of stack character starts on the stack. So in this case, an initial state doesn't have to have absolutely nothing on the stack. And as long as you're consistent, you can terminate with the bottom of stack character still on the stack. Yeah.
If we are using some cases where it isn't using the bottom of the stack, how should that be, or bottom of the stack character, how should it be written that the stack is empty? If that makes sense.
Yeah. It's okay as long as what the stack contains is nothing at the end of this. So if you replace this Z with a lambda, this would just say we pop the Z and push nothing, which means there is nothing on the stack, not even the bottom of stack character. And that's good enough to just see that when there is nothing on the stack, that we're good. There just is no notational way to define something with regards to nothing on the stack. So once you have nothing on the stack, you either must be at the very beginning and about to push the bottom of stack character, or at the very end about to accept. The stack should not be empty at any point in the middle of that. That bottom of stack character is what tells you that the stack is empty, even though there is a character on the stack. It's like the is empty returning true. It's your call to is empty when you look for that character. Questions on instantaneous descriptions? Questions what any of these mean or why this is a parse for BAAB? It defines exactly the states and transitions that we took while defining that.
Why is it on lambda that for the last term state, QF lambda Z? Why are we not popping Z?
We could, it's an option, but notationally, you'll sometimes see it one way, notationally, you'll sometimes see it the other.
Oh, okay.
So even the book is not consistent between whether the bottom of stack character is on or off, which annoys me. So either one is fine. I know what you mean and the grader knows what you mean, but try to be consistent between the bottom of stack character being there as part of your acceptance or the bottom of stack character being removed as part of your acceptance. However it is that you would prefer that. It's typically one state less this way because you don't have to put the bottom of stack character on the stack, but taking it off is the equivalent transition. You just turn this last Z into a lambda. Good question. Any others? I'll assume this makes sense then. Anyone need anything else from the board before it goes away? Yeah, it's gone. All right, this just tells us what I just wrote. Again, we have those three conditions in order to accept. We need to end in a final state with an empty stack. And again, you can define that as either the bottom of stack symbol is on the stack or the bottom of stack symbol has been removed from the stack. And we have to be at the end of the input string, which we are. According to the instantaneous description, there's that lambda in the middle that tells us that we are at the end of the input string. All right, we ready to build another NPDA? Here is your example. It's a familiar one to us. String followed by that same string in reverse. This was an example that we've used to show that it's not regular, but in fact, perhaps it is context-free. In fact, we did show that it's context-free within the scope of the wrote a grammar for it. So if we were able to write a context-free grammar for it, we should be able to draw an NPDA for it. So again, the way that I recommend proceeding here is thinking algorithmically. If you were to write a program to recognize a string that was in this language, how would you proceed? And when I say algorithmically, since we're carrying a stack along with us, think how you would use a stack to solve this problem. Wherever it is that you get stuck, get unstuck with non-determinism. Anyone want to describe a broad solution that they're thinking of? Just in English as a summary, what would your idea of a solution be?
Adding ones when an A is read and taking off ones when an A is read, or sorry, from 0 to 1, adding a 1 for A or a 0 for B, and then from 1 to 2, popping it up.
Okay. So something like, if we were to split this string into W and WR, we should have a state for pushing things onto the stack to read W, and then a state to pop those things off when we're reading WR. But we need to know, when do we switch from reading W to reading WR? That is the algorithmic trick. That would be what is difficult to do by writing a program. And that is what non-determinism will help with. Wherever the middle of the string is, that is where we transition. We are forking processes after every single character saying, is this the middle of the string? And you're going to go attempt to verify that with another process. And a lot of those processes will fail because we didn't guess the middle of the string correctly. But on that one that guesses it correctly, it will finish in the final state at the correct time and place to be able to accept. Since one of those threads moved to acceptance, then we accept the whole thing. So yeah, we want to push all characters for W onto the stack, and then pop all characters from the reverse string off the stack. Let's spend a little bit more time and finish this off. How is this going? Do people feel like they can work through at least to the point of getting stuck somewhere? Looks like we could use a walkthrough. Let's talk it through. So this says to write the transition function. I'm going to draw it out as a state machine because I think that is a little bit more visual, helps people a little bit more to do that. So like before, I'm going to assume that in our initial state, we have the bottom of stack character already there. So from Q0, the very first thing we need to do is start reading symbols from W. Since this was AB plus as the language, we know there's at least one character. We don't have to worry about carrying through a 0 character solution. The empty string would be a WWR, both W and WR being the empty string. It's not in the language, thankfully. There is a way to make that work, but it's an unnecessary complication. So we need to be able to handle adding W to the stack here. That's going to involve quite a few transitions. So let's think them through. The very first thing that we could see, we know that Z is on the stack initially. So if we read an A and there's a Z on the stack, we can use a stack alphabet of 0, 1 again, 0 representing an A, 1 representing a B. Or we could just continue to use A's and B's, capital A's and B's, doesn't really matter. But I'm going to carry through using binary. So if we see an A that's part of W, we need to put an associated 0 on the stack. And similarly, maybe I'll do my B's down below. If we see a B with a Z on top of the stack, we're going to add a 1 to the stack, saying that wherever it is that we see this A or B, there needs to be an associated place at the end of the string that also sees this. So if our string starts with an A, if it's in this language, wherever it terminates, there is a matching A somewhere. If it starts with a B, there's a matching B at the end of the string that we'll need to be able to see when we are popping off characters reading WR. So those are our transitions that specify on Z, but those aren't the only ones for where we could be when we're reading W. There could be a 0 on top of the stack, because the first thing we do is throw a 0 on top of the stack. Then we have to be able to read A's and B's as long as W is more than one character. So if we read an A and there is a 0 on top of the stack, we should add another one. If we read a B and there is a 0 on top of the stack, we should throw a 1 on top of that 0. Likewise, we could have put a 1 on top of the stack. If we did that and our first character was a B, we need to be able to handle, how do we handle 1s being on top of the stack? So we could read an A with a 1 on top of the stack, throw a 0 on top of that 1. B, if there's a 1 on top of the stack, we need the ability to add an extra 1 on top of that. These are all of the transitions that are needed to define W. If we did this, we would just build a stack of all of the characters of the string. That's not quite what we want to do. So we need at some point to transition instead of pushing characters onto the stack. We need to start popping characters off of the stack. We have a couple of options here. Since this is the string AB plus, we could say on this transition, that is the transition that reads the first character, that pops the first character off the stack. Or we could say, let's just basically do a no-op, do nothing, and teleport from Q0 to Q1 at the middle point. Anyone have a preference of how we proceed with this? Solutions could use either way. Do we like the teleportation in the middle of the string idea, or do we like the recognize the first character of the second half of the string, transition on that character? The idea makes more intuitive sense. The teleportation idea for non-determinism. So when we hit the middle of the string, we're just going to loop ourselves over to Q1. Excellent. So to do that, we read nothing from the input. We pop nothing from the stack, and we push nothing to the stack. This is a complete and total no-op. We do absolutely nothing and freely transition from Q0 to Q1. What that means is that at every single point here, we are going to have to determine where it is that we do that. We'll have to check that at every single point. This would be the solution for AB star, not AB plus. We need to ensure that we at least read a single character here, otherwise the language would be AB star. So I didn't want to go through this, but the correct solution for AB plus is the other way, is to ensure that we pop off a character, which forces that we pushed on a single character. But again, this is how you would know up, this is how you would teleport. Since this is plus, I lied, there is a correct answer to this. We have to pop the first character off. There are two ways to pop off the first character of WR. The question is, was that first character an A or a B? And regardless, we're going to need the associated character that we read to be on the stack. So if we read an A, we are going to pop a 0 from the stack and push nothing. Or we could read a B, pop a 1, push nothing. This forces the character that we remove from the top of the stack to be the character that we are reading. That forces somewhere in the middle there to be some sequence of characters where the last character that we pushed to the stack would be a 1, and the first character that we pop would also be a 1. So if we read a B, a 1 has to be on top of the stack. If we read an A 0 has to be on top of the stack. That's what creates that necessary character pair in the middle. Now we reach Q1. This is not final yet because we have to have an empty stack before we can end up with a final state. So in Q1, we need the rules for how to pop off of the stack. It's going to look very much like this. We could either read an A with a 0 on top of the stack and pop it freely. We could read a B with a 1 on top of the stack and pop it freely. We cannot read an A with a 1 on top of the stack. That would not be good. We cannot read a B with a 0 on top of the stack. That would not be good. That would say that this string is not a palindrome. It's not an even length palindrome, and we should terminate immediately. From here, this will eventually clear the stack, assuming that the language, the string we're reading is actually WWR. If it is that for this particular path through this NPDA, then this will empty the stack, leaving us with the bottom of stack character. When we reach that point, we should be able to freely transition, reading nothing, removing the bottom of stack character, and we can say pushing it back on, that's just fine. And we will move to a final QF that we can accept once we reach that bottom of stack character. This completes the solution. Any questions on this construction? We're going to run through an example of it with a string here in a second. But does anyone have any questions about the notation or the construction of this NPDA? How close were you? Not close. Excellent. We need more practice. does the logic of the construction, I try to justify each step that I take as I put it together as to why that works. Does that make sense? Do you feel like if I gave you the same, exactly this problem in a couple of days, that you'd be able to recreate this solution? I feel like that's a good place to be right now. All right, let's walk through with some examples to see exactly how this solution works with a given string. So let's start with an example that adheres to WWR. Someone give me a string that does that. What's a string that's in this language?
A, B, B, A.
A, B, B, A. I'm going to start drawing this as kind of a tree, just so that we see what all of these non-deterministic processes look like that get forked and then fail, because that's important. So let's start this process. We're going to build what is like the instantaneous description for this. So we're going to keep a local stack with us as we look at a tree of possibilities from here. So from Q0, we know that when we begin this, we haven't read anything, and our stack just has a Z on it. What are the options? Are there options for how to proceed from here, given our NPDA? There's only one thing we can do, which is nice. We can't take this transition because there is not a 0 or 1 on the stack. And there is a Z on the stack, which narrows us down to just these two. And given that the first character is an A, we have to read it. So that tells us that this is the transition that we are going to take right here. So in this tree, there is only a single branch down to, we're going to read this A, giving us B, B, A, and a stack that is now a Z with a 0 on top. Are there any options for how to proceed? There is one option,
Well, yeah.
staying in Q0, but there's not more than one option. It's probably, there's only going to be one path through for this entire string. But let's just walk through and see that path and see that work. So with a 0, when we're reading a B, again, there's nothing we can do transitioning to Q1. When there's a 0 on top of the stack and we read a B, we push a 1 on top of that. That's the only transition that we can make here. So there is BA left in the string, and our stack now is a Z with a 0 and a 1. Now we can finally split. So this is going to start forking. I'm going to start forking this way on the board because I'm running out of space down here already. But from this BA, we don't know if we're at the middle of the string or if there is more to W. Since we can't look that far ahead, we just read, this is a B. Is it the middle of the string? Have we reached the middle of the string? We don't know yet. The answer is yes, but there's no way for us to know that as the program. So we're going to split into two. One of them is going to continue reading W, and one of them is going to guess that we have reached the middle point in the string and start verifying that what remains in the string is WR. So this string is going to keep reading W, and this is going to read WR. So if this is W, what is left is A. And if this is still W, this B, when there's a 1 on top of the stack, there's a legal transition here that adds a 1 to that. So our stack that we're carrying along with us is a Z followed by the 0 and the 1, and we're going to add another 1 on top of it. Great. That process will do its thing. There was another option here, though. So we need to fork another child that's going to read the B and take this transition with a 1 on top of the stack that says this is the first legal character of WR. So this A is going to have a stack that's the Z, the 0, and instead of adding a 1, we're going to take this 1 off, getting to that point. So when we do that, we transition to Q1. This stayed in Q0, and we were in Q0 at each of these points. Now you can see how this is exactly what the instantaneous description tells us as to why this is important. It's exactly the information that we need. It's the state that we're in, the string that we have left to read, the unread portion of the string, and the stacked contents. So I'm really walking through instantaneous descriptions as we do this. Yeah,
How would you write the split in the notation for the?
you wouldn't. The instantaneous description already assumes that the path that we are showing is the path to acceptance. So you would identify the path. But in reality, what we're doing is we're exploring all options with non-determinism. All right, from this state, we've read the A. All that's left of us here is we've read this B. We have an A left. So we again have to decide, is this W or are we starting to read WR? There is no possibility to start reading WR because we need to read an A with a 1 on top of the stack. There is no way to do that in transition to Q1. So the only thing we can do here is assume that the next character is still part of W. So we do this. We see that we're at the end of the string. We are in Q0 still, and we have a very large stack of Z, 0, 1, 1, 0. From this point, there's a 0 on top of the stack, and we're in Q1. So we can either see the bottom of stack character in transition, which is not on top of the stack, or we can read an A and see a 0 on top of the stack, which we see the A, there's a 0 on top of the stack. That tells us that that is the single thing that we can do here. So we're going to read that A, giving us lambda, and our stack now is back to just having the bottom of the stack character on. From here, we need a transition from Q0 that reads nothing from the input because there's nothing left in the input. And from Q0, there's not a single transition that does not read a character in the input. So because of that, this thread dies. There is no move for us to make. This thread will reject and say that this path through this is not WWR. Here, though, we're in Q1. We need a transition that reads nothing with the bottom of stack character as a Z. So we can transition now from Q1 to QF, nothing to read, and the stack just having that bottom of stack character on it, which is the necessary requirements for acceptance. So this thread accepts. And since there is a path through this that accepts, the entire string is accepted as WWR. There was a midpoint such that the first half was W and the second half was WR. Questions on that process and kind of seeing how the process forking works? Yeah.
So could we have any amount of things on the stack at the end? Final settings.
It has to be an empty stack.
Empty stack. So like 0 or 1 Z's.
Yeah. It has to be, there's no other way to put a Z on the stack. It's kind of it is the character that tells you that the stack is empty.
So if it's in the final state, but the stack is empty when the stack is not empty when the string ends, then it's considered to not have accepted.
Yes, as long as there's no transition within QF. If you want to be able to accept when that happens, then you would just add a self edge to QF that removes things from the stack. Which you could absolutely do. Say, I'm not going to read anything from the string, and I'm going to pop whatever is on the stack. So you could define that if that's what you want. But as a state machine designer, we want to be able to distinguish between if there is stuff left on the stack. Like for instance, here we could have ended up, or close to ended up in a final state, in the final state, if we somehow were able to do that. Or another example to this is if WWR exists in the first part of the string. Like if we had A, B, B, A, B, B, A. Now we have a recursive WWR where there's W, there's WR, there's W, there's WR. So if we had such a string like this, there would be a thread that goes ABBA and ends up in QF at that point. But since there's still characters to read, we're not at the end of the string, we don't want to accept that, saying there exists a WWR somewhere in the string. We want to determine if the entire string is a WWR. So that's a related question that we don't want to confuse with our question. So that's why we have to be in the final state, and we have to be at the end of the string in order to do so. You could still have some things on the stack and be in the final state. Not in this problem, but in other problems you might be able to do that. And that would tell us that we've parsed part of the string, we parsed the entire string, and if there were more of the string, we could possibly see the rest of the route to acceptance. But since the string ended there, we don't want to accept yet. Yeah.
For each of these edges, are we restricted to only consuming one character off the top of the stack? Like,
Yeah, we can only peek at the top character. So you can push arbitrary numbers of characters onto the stack, but you can only pop a single character off the stack. And you can only read a single character at a time, just like with a DFA or NFA as well. So the only shortcut we allow are multi-pushes. Otherwise, you can divide it into multiple transitions. If you wanted to do a multi-pop, you absolutely could. You just have to define it as multiple transitions.
So we can multi-push but not multi-pop.
Correct. So in this case, we are really doing the equivalent of a single push, but it's always defined in terms of a pop, because that identifies the character that needs to be on top of the stack in order to make that transition. And then we push that back with some more characters, but there's nothing that limits us to a single push. We could push 5 characters on the stack if we wanted to. That is allowed. But since we can't dig multiple characters down into the stack, we can't allow for there to be extra memory. So if we care about the top 2 characters of the stack, we'd have to look at the top character of the stack, place that somewhere, look at the next character of the stack. We don't have that extra memory. The only memory we have is the stack. So we need 2 transitions to be defined of, let's look at the top character of the stack, make the transition, then look at the new top character of the stack, make another transition. And that doesn't require the extra memory that we would need for a multi-pop. How are we doing? Questions on any of this? Do we feel a little bit better about walking through NPDAs with an example like this that kind of shows, especially non-deterministically, what happens when we reach something like a branching point? We have to fork multiple processes and carry those processes through their options, and each one of those processes will either accept or reject, and we're just looking for the one thread that accepts. Right. Very good. All right. So the slides give you the written rules, the written transition rules for this, and that's just fine. It allows you kind of like writing a program to signify methods. And the methods are defined as the states that we drew before, but now they're labeled as the rules for pushing the string onto the stack, the rules for guessing the middle of the string, the rules for matching the reverse string against the stack, and the rules for recognizing termination that we have a WWR. That's what our states represented, but it's difficult to label your states. Q pushing W onto the stack. Q guessing the middle of the string. It's a little bit easier to write kind of like assembly labels and rules that associate with that label. So now you can kind of also see why assembly is created or structured the way that it is it's very much like this. This is very assembly level logic. So we don't really have a ton of time to go into the next thing, but the next thing we are going to tackle is the translation of context-free grammars into NPDAs. So given that we have a context-free grammar, how do we make one of these automata out of it? And we will see that this is the reason that Greibach normoform exists. So we'll come back to that and see this tomorrow. Office hour starting now for anyone who'd like to work on some homework.
For sure.